All right, so let's talk about this one, dimensionality reduction, which I mentioned before. And this is an interesting phenomenon. Now, if you have two dimensions, like an X and a Y, and you pick a random point, the random point is likely to be somewhere in the middle and not at one of the edges. But if you have more dimensions, that changes. Um, if you think about it, if I have, say, 100 dimensions, then I'm going to pick 100 random values, say between 0 and 1. So if I have a 100-dimensional hypercube from 0 to 1 in 100 dimensions, if any one of those 100 guesses is near an edge, then I'm on the surface of that cube. That cube has a lot of surface. Now, the reason why this matters is think about trying to trace out a curve. Like if this is from 0 to 1 across the screen, and I want to trace it out, I don't want one point at this edge and one point at that edge. I need to have some points in the middle to trace out the curve. Logically, I would need to have maybe 10 points across the width of this curve to trace out the shape. So it's not enough to just have points on the edge of the hypercube. You have to have points in the middle, and that turns out to be essentially impossible. So here, you can just do it by brute force. You can pick random numbers for all the coordinates and see how many points are on the edge. And I define the edge as being less than 0.01 or greater than 0.99. So 99% of the way over to the edge. And if you count how many out of 100, out of 1,000 are there, for 2, 3, and 10 dimensions, it's okay. But by the time you get to 1,000 dimensions, all of the points are on the edge. Therefore, no matter how much data you have, you cannot possibly have enough data to ever describe any real phenomenon in that number of dimensions. This is the fundamental mathematical fact that if you, and like I said, think about a Tesla. A Tesla's got a camera taking 4,000 pixels by 4,000 pixels 30 times a second all the time. So you have millions of dimensions. You're off the bottom here. So if you tried to train on all those dimensions, you couldn't possibly do it. You couldn't possibly have a representative sample of points to trace out the dependence of anything. So you can't do it this way. And this is not what your brain does. What your brain does, which is faced with exactly the same problem, far too much data, is it pre-processes it using simple techniques to figure out what's important and focus only on the important part of what you see. And that's why there's a famous demonstration you've probably seen where they ask people to watch people passing a basketball around. And right in the middle of that, a guy wearing a gorilla suit rides a unicycle through it. And most people never see the gorilla because they're told to watch the ball. So they focus on the ball and their brain ignores everything else as irrelevant. And the same thing's true in courtrooms. Courtroom testimony shows that if you ask people, did you see the bad guy do this thing? What clothes were they wearing? What color was their hair? You get all sorts of stupid answers because people only remember the little bit of information they were paying attention to, and they sort of make up the rest like a large language model. They sort of fill it in, even though they didn't really notice it. So this is an essential job, is how are we going to lower the number of dimensions? And by the way, you can look at it another way. You can count the edge points, or you can calculate the distance between points in various dimensions. And as you can see, once you get above about 1,000, and this is a unit hypercube, so the actual, each parameter only goes from 0 to 1, and yet the distance between points is now 12 or 100 or 400, clearly showing you that I don't possibly have enough data to trace out the shape of a curve in that space, not even remotely. So you use principal component analysis, a statistical technique that is well established. So here we take data sets like we've seen before, handwritten digits, and after we get a bunch of them, 60,000 of them, each one of them has far too many points, 28 by 28. So it's the original data has 792 pixels in each image. And I don't really want to work in a 792 dimensional space. So we can ask, how many of those 792 dimensions do you really need? And you do it with principal component analysis, and it's really very simple. You measure how much of the variance can be captured with only some of the parameters. It's just a correlation coefficient kind of thing. And it turns out that if you want to catch 95% of the variance, you need 154 dimensions, not the original 784. And all you do is you plot all the data in that 784 dimensional space, and you take the directions where you find the most variation. That's what principal component analysis does. And then you tick that out and pick that out and see how much is left. So you can explain 95% of the actual information in that data with only 154 dimensions. All right. And so now, first we're going to reduce the dimensions and then classify using a random forest, which is just a bunch of decision trees. So first here's a random forest classifier. And so what happens is you can evaluate, you can achieve 85% by using 23 dimensions. And it did that by making 465 decision trees and making a forest out of them and averaging them together to cause the various errors to cancel out. So that's what happened here. And then you can go back and see what you've done. I only kept 23 dimensions out of the 784 dimensions in the original data. So you might wonder how much harm does it do the data. And this is what happens if you keep only the significant dimensions. This is what we kept. And as you can see, it has lost some details for a lot of these images, but this turns out to be like 80 or 90% effective. I think it turned out to be 85% accurate. So that's what you do. That's principal component analysis and reducing dimensions. And this is an essential activity. You could never get anything meaningful done without it. Stop this one.